experience in the areas of radar, electronic warfare, electromagnetic effects on electronics, and also directed energy weapons and their effects. I spent 37 years at the Army Research Laboratory in Adelphi, Maryland, and then I have been with the service engineering for the last 8 years. Today, we're going to talk about one of the forms of directed energy weapons, namely the high power radio frequency / microwave, HPM for short, although there's lots of different names, as I'll show in a moment, directed energy weapons and their effects. The next slide is an outline, and what we're going to cover today is basics of what are HPM directed energy weapons, why are they important to the warfighter, how are HPM weapons different than high energy lasers, and how are HPM directed energies similar to electronic warfare, traditional electronic warfare, but different. Also, how are our high power directed energy weapons similar to but different from nuclear generated electromagnetic pulse. When we're going to talk about how HPM couples into a target, what type of effects it can cause, a brief description of how we can protect our systems against HPM pulses, and then a summary and questions. This next slide gives you a definition of what a high power radio frequency microwave directed energy weapon is. In the community, it's also known as a number of other names that can be confusing if people don't realize they're all talking similar things. Some of those names are such things as electromagnetic weapons, RF weapons, non-nuclear EMP, electronic bombs, etc. The main definition is that HPM DUs are electromagnetic sources that can generate and direct intense radio frequency microwave energy at a target. It says electronic target there, but actually it's to be more general, since there are some non-lethal directed energy weapons that could also be other types of targets. There's no direct definition for what's the difference between a high-power microwave DU and a radar, but we've attempted to basically have a dividing point of that if a source has a peak effective radiated power of greater than 100 megawatts or radiated energy of greater than 1 joule per second, it typically would fall into the area of high power microwave sources. The range of frequencies of these sources can vary significantly depending upon what you're talking about. As it shows there, you're talking anywhere from the electromagnetic spectrum of high frequency to very high frequency, to ultra high frequency, to microwaves, to millimeter waves. And the most important thing to remember about HPM DUs, the takeaway from all of this, is that they can attack targets with and without intentional antennas and receivers. That's unlike traditional electronic warfare jammers. They also can produce persistent effects that last much longer than the time the beam is on the target. As a result, they can produce temporary electronic upset, or if there's significant energy damage. As a result of this, we call this sometimes unconventional electronic attack, and we'll explain more about that later. The next slide shows the major components of a high-power microwave directed energy weapon. Those of you familiar with radar will see a similarity as far as the source goes. Typically, in any system, you've got to have some form of prime power. That prime power could be an electrical generator, it could be a battery pack, or it could be the potential of using explosives to try to generate the energy necessary. The prime power must then be conditioned to produce pulses, and the pulse powers typically are some sort of a capacitive inductive type of network, such as a pulse forming network, or in some sources it may be high power switches, either high power switch tubes or solid state. As far as the RF source goes, there's two typical types of RF sources. Those that produce pulse continuous wave energy, and since in the frequency domain that's a narrow band, they're called narrow band sources. Examples of narrow band sources are magnetrons, traveling wave tube amplifiers, klystron amplifiers, and gyrotron types of sources. There's also the other type of RF source, which we'll go into in more detail, is a transient source, if you will, an impulse type of source. As a result, in the frequency domain, that produces a very wide band to ultra wide band of frequencies. That typically is some form of a spark gap, electronic switch, or ferrite lines. There's also now, I don't cover this in the presentation, but nonlinear transmission line types of devices that are becoming of great interest. Now we need, of course, an antenna in order to get the RF energy out of the HPMD to the target. In terms of antennas, again, there were kind of two major categories. For narrowband antennas, one of the typical ways of doing that is with high power aperture antennas, such as parabolic reflectors, horns, and those type of things. They typically are going to be for the higher frequencies, starting with the microwaves regime of either 1 gigahertz on up or below that. And they typically will have a high gain and high directivity depending upon the size of the aperture. The amount of gain of an antenna is directly proportionate to the size of the antenna aperture, the physical size of the aperture, and then inversely to the wavelength. The good thing about a narrowband antenna is it normally produces a well-defined pattern so that you can very much know off boresight what it is. The next type of antenna is what we call a wideband antenna, and of course that goes with wideband sources. Because the wideband sources produce such a wide variety of frequency, the type of antenna here is typically some sort of either dipole, monopole, or some sort of transverse electromagnetic horn. They tend to be in the lower frequencies, more like in the VHF, UHF range. The antenna tends to have less gain, and the off-site, the off-boresight pattern is more difficult to determine. Then, of course, the RF energy must propagate out of the antenna through the environment to the target. Through the environment, the main loss is the range, because the energy will decrease as 1 over the range squared as it moves out from the source. There is also atmospheric losses. Fortunately, in the microwave regime and lower, they tend to not be that great unless there's tremendous weather conditions of rain and such as that. Once the energy hits the target, we have the target there represented as a simplistic picture of some sort of a port of entry for the RF energy to get into the target. Some form a coupling path from the port of entry down to the component, and then the component itself. And we'll talk more about that later.
Hey, John, this is Brian. Can I interrupt for just a moment?
Yes.
Okay, just want to let everybody know, please, what I'm going to do is I'm going to mute everyone's microphone, and then I'll unmute them at the end for the Q&A, just so we can get rid of that background chatter. Unmute. Okay, John, you back? You ready to go? John, are you there though? Make sure I didn't mute you.
I'm sorry. Can you hear me now?
Yep, go ahead. All right, so we're good to go.
Okay. Were the people able to hear me for the other slides? I apologize. I may have had this muted.
Yes, no, you were good. I just wanted to eliminate the background chatter from all the other folks.
Okay. Why is HPM dues, why are we investing money and time and effort in it? Well, obviously, if it wasn't useful in some way to the warfighter, the peacekeepers, we would not be doing that. One of the major things that high power microwave directed energy weapons brings to the table is and directed energy in general, is that it's able to engage targets at the speed of light. That means instantaneous fly out, no need for lead angles, and that type of thing that you have to worry about with kinetic energy weapons. However, it must be emphasized that even though the engagement can be at the speed of light, the effect may not be instantaneous. It may be necessary to dwell on the target for seconds to minutes, depending upon what the application is. The other important thing about RF directed energy weapons is that you could produce, to some extent, scalable effects from temporary upset to permanent damage based on the target and how far away the source is from the target. As a result, you've got the potential to have a scalable type or tunable target effects. The most important part, and the reason primarily that people are interested in this technology, is that a directed energy weapon provides a very deep magazine to a warfighter with relatively unlimited number of low-cost shots, DE pulses. The basic thing that you need is to have fuel for the platform that the HPM weapon is on, and as long as that fuel and electrical power remain, then you can keep engaging targets. This greatly reduces logistics and the associated cost of happening, and also the concern about you losing all of your weapons and have to reload. Another important part about HPM is because you're talking about a relatively wide beam, this provides a very high probability of hit on a target that is compared to either a kinetic energy weapon or a laser, where you're going to need to be able to have a high probability of hit in order to have the effect. It also allows you for plausible deniability. Since electromagnetic energy cannot be seen, cannot be felt, cannot be tasted, it can be felt in a certain way, it's important that you could basically actually cause an adversary to have electronic failure and not immediately be able to figure out what that is. Typically, we talk about electromagnetic waves being used against electronic weapons, such as sensors and communication systems and all of that. Its operation is similar to a radar. However, it's much higher peak powers, as I mentioned. So at least the operation and maintenance, in theory, can be along the lines of someone who is skilled as a radar technician and does not necessarily require a separate military operational specialty. Now, most of the things we've talked about have been electronic so far, but the other thing that we need to discuss is the fact that depending upon what frequency the HPM do is, as long as it's relatively low frequency, below 35 gigahertz, it's typically non-lethal to humans unless there's long exposure times. What we know as far as safety levels and all go is based on the IEEE RF radiation safety standards, which concerns the amount of not only the amount of average power, but the amount of dwell time. So generally speaking, since the pulses are very short and the rep rates are relatively small, the average power is not that high unless you have a long dwell time. On the other hand, as you may have heard, there's the U.S. Air Force Research Lab developed a system called the Area Denial System that the Joint Non-Lethal Weapons Directorate sponsored and carried forth. And that's a system that uses millimeter waves, roughly at 95 gigahertz. And they discovered that at 95 gigahertz, the energy can actually penetrate the skin and stimulate the nerves underneath the skin to give the simulation of a burn, of actually heating. As a result, that provides a way to control humans in a non-lethal way, because seems to be a significant difference between the threshold required to cause the intense pain and that for human damage. So this allows people, the warfighter and peacekeepers, to now have a weapon system that can actually radiate personnel to keep them back or to keep them from a certain area, such as protecting a high-value asset. And that pain will go away if they back off or if the energy is turned off. That's very important because that's a new application that appears to be of great interest, not only to the United States, but to our allies and unfortunately to our adversaries also. The last thing I'll say about that is that everybody says, oh, well, we can just easily protect against high power microwave weapons by wrapping it in tin foil or something of that nature, creating a Faraday shield. The issue there is that in theory, that is very easy to do. I mean, it's very easy to do theoretically, but it may be very difficult in practice, because it turns out where you put the shielding can redistribute the electromagnetic fields inside the target. And if you're not careful, you could actually increase the amount of energy at a particular place as opposed to trying to decrease it. The next slide just gives a cartoon picture of some of the applications of directed energy weapons as a whole. Those where you see red lines, they represent high energy lasers. And of course, high energy lasers is one of the major components of directed energy weapons. The high energy laser emits very high intense photons, light onto a target, typically in the invisible range, and is so intense that it can actually cause structural damage to a target in terms of the intense heat that it produces. The other systems you see there, where there are kind of little waves going out, that represents the HPM. In recent years, there have been tremendous advances in the laser community with high energy lasers, to the point that now they are actually feasible to be used in some air defense applications. Those are being looked at very heavily by all three services, and the Navy in particular is planning on actually installing a high energy laser on a ship for being able to protect against low-cost targets, swarm low-cost types of targets. The Army's very interested in that also and has plans, and the Air Force is also very interested in using lasers, possibly for not only base defense, but also for aircraft survivability against missiles. The main uses for high power microwave at current are those where you have a relatively short distance, such as countermine, counter IED, and also for the possibility of stopping vehicles with electronic engine control systems. Now there's also the fact that the HPM is looking very successful against being able to engage unmanned aerial aircraft and to disrupt their control and electronic systems sufficient to make them either catastrophically crash or to not be able to perform their mission. Next slide talks about what are some of the enablers for directed energy weapon. We talked about some of the advantages of directed energy weapon, but we also know that that was basically, up until recently, there has not been sufficient power and energy on the platforms capable to do this. A combination of bringing the power and energy requirements for the directed energy weapon down as much as possible. And the most important part is the idea that all three services are now involved with electrical power systems for the ships, aircraft, and vehicles. In the past, there would not have been sufficient energy to power a directed energy weapon, so an extra generator would have had to be added, but now there's the potential that there could be an electronic platform that can provide all of the energy necessary, and it's more a issue of energy control as opposed to not having enough energy. I use the analogy of Star Trek, which dates me, but it's kind of like now they can actually say, okay, do we want to use the power for our mobility? Do we want to put the shields up, or do we want to use the weapons? We talked about the types of HPM sources, but here I'll describe again briefly what the two different types are. As you can see in the picture, there's a time domain version of what the HPM pulse looks like, and then the frequency domain. For narrowband, you're talking about typical pulse modulated sine waves. So in the frequency domain, that turns out to be some sort of a kind of sine x over x function, a sync function aimed at the particular carrier frequency of the wave. And as a result, it's very narrow band, and there's therefore the name. The advantages of a narrowband signal is that it's best for maximizing the amount of energy per pulse. But often you do not know the type of frequency that you want to use against a target. So the wideband, which is more of a unipolar type of waveform that provides a damp sine wave in the time domain, and it's a much broader frequency domain. This is more like, if you will, the traditional electromagnetic pulse from a nuclear weapon. However, now there's the capability of generating these very high powers with with non-nuclear waves. This has a tendency, it's best for maximizing the power, but it also is, since you're spreading the energy out over a larger band, you are losing the amount of energy. So it's kind of depends on what the particular application that is best. The next slide just shows some examples to show some real world systems that are actually been considered. And you'll see we have the power supply driving some sort of an HPM source and transmitter and the antenna. The most recent advantage that we know of as far as an HPM system is the U.S. Air Force has recently fielded or developed and fielded a tactical high-power microwave operational responder for going after unmanned aerial vehicles, THOR. You see where the P and the S is indicating power sources, the source, and the antenna. At a much smaller level, the Army developed for the Navy a long time ago a small truck-mounted narrowband HPM source to help them demonstrate demonstrate that a source of this type that could be covered and covert could be able to be driven by buildings with electronics and potentially affect them in a negative way. Another source is the Air Force's ultra-wideband source with an impulse radiating antenna, which provides the potential for some ground defense.
And hey, John, this is Brian. Just a quick time check. You know, so it's about 12:30 here. I want to see if, not to rush you too much, but see if you can try to wrap this up in the next 5 or 10 minutes. We do have some time for Q&A at the end.
Yes, I certainly will. Thank you. As I mentioned before, this is a this is a chart that describes electronic warfare. Electronic warfare is defined as electronic protect, electronic attack, and electronic support. Under electronic attack, in the past, we've always had, everyone is aware of jammers to go after radar and communication receivers. They must be some sort of receiver on the target for them to work. And they produce temporary effects only while the RF is on. UEA on the other side, unconventional electronic attack, including directed energy weapons, provides persistent effects on all electronics.
Oh, John, you still there? Sounds like the audio dropped a little bit. John, I'm not sure if you can hear me or not, but the audio is kind of coming in and out.
Can you hear me?
Yes, there you go. You're back.
Okay, good. So anyway, this just shows the different types of effects that can occur with directed energy weapons. The next view graph is it shows the electronic attack technology that is being considered. And if you look at the y-axis as the RF power density on target and what the target response is, as you can see, it depends on what your mission is or what your goal is to be able to, whether you're going to have to use very high peak power densities, which are going to be typically some sort of high power RF tube shown in the dark green, or if you're looking for interference, electronic warfare, upset types of things, where you have the potential now of replacing some of the high power RF tubes with solid state RF amplifiers. Gallium nitride amplifiers have provided a tremendous advance in technology in the ability to build high power types of transmitters, but still when you need energy up into the hundreds of watts per square centimeter and kilowatts, you're typically going to have to use some sort of an RF power tube. Quickly, I'll go over what is HPM and what is EMP. The main differences is that typically the nuclear EMP, traditional nuclear EMP, is a single shot phenomenon, while HPM may be repetitively pulsed. The frequency regimes differ, so the resonant coupling and energy is a tremendous difference. I will show a chart in a moment, so I'll leave the other here. The other thing is that both address complex RF coupling into targets, and they require numerous it's basically you're concerned with many parameters to describe the effects, and there are limited facilities and test objects sometimes that you can get. That you normally would like to try to get the test objects and actually test them directly if you can. The other important thing is that the nuclear EMP threat is basically, if you will, an official threat that has a well-defined waveform to it. As a result, you can actually generate devices that simulate the HPM, the EMP threat, and test the system against them. With HPM, you cannot do that because the HPM threat can vary over a wide range of frequencies and pulse widths and PRFs. Here shows a plot of power density versus frequency, and here it attempts to try to compare the spectrum for a nuclear EMP type of system to, if you will, HPM. Now for HPM here, as I mentioned before, since there's not a one specific well-defined threat, I've used the mill standard 460 Ford shipboard electromagnetic environment to show that even some of these sources that are on ships these days can produce power densities up into the levels of what we're concerned about threat energy. So for people who say there is no validated threat, we don't have to worry about it, unfortunately, that's not true. There are adversaries out there pursuing this, and we also have our own threat of electromagnetic interference. Okay, how does energy couple into a target? There are two main ways. One is through the antenna, and that can be either what we call in-band front door or out-of-band front door. If it's in-band, it means that the RF energy is in the frequency range of the system. It goes through the normal antenna, path loss, and down to the component. If it's out-of-band, it can still come in through the antenna. However, typically the antenna is not going to provide anywhere near the gain directivity that it does for in-band energy. And it can also couple in through what we call unintentional types of ports of entry or backdoors, such as aperture seams, couples into the electronics either through radiation to the components themselves or couples in through wires down to the components. What are the effects? We've talked about that briefly, so I won't go over this, but it just basically you can cause temporary interference where we define where the system recovers when the beam is removed, longer term upset, which normally requires some sort of operator intervention or permanent damage. The important thing is that all of these effects are statistical quantities that are best expressed in terms of probability of effect as opposed to effect thresholds. These are the types of experiments that can be done. You can do free field experiments, which is the most representative of an outdoor type of scenario where you radiate the target in a chamber or outdoors with HPM sources and observe and see what the responses are. At the same time, you're limited because the number of sources and their parameters are limited. So sometimes if you're lucky enough to be able to do the proper analysis, you could actually do direct driving experiments where you need less power to cause the effect, and you can evaluate the sensitivity of pulse width and PRF. This is just an electronic attack scenario thing. What we're trying to do here is show that there is a way of at least estimating potentially the type of power density that you need on the target. We have here the electronic attack target, electronic attack transmitter, the antenna. The power density that's incident on the antenna is defined by the power of the transmitter, peak power or average, times the gain over 4 pi r squared. That's the range loss. That energy you would also add for propagation if you're talking about frequencies that are higher. You need to include the atmospheric losses. And then that energy impinges upon the target, and there we use the target represented as the effective area of the port of entry, the entry path or the loss, and the electronics component failure level. What you're trying to do is look at what is the power that is actually down at the component as compared to the component failure level. Both of these are actually statistical quantities, And since you have really what you're looking at is the probability of RF damage, is the probability that the energy at the component is greater than the component, and that can be looked at as a convolution integral as of the convolution of the probability density function of the coupling times the probability distribution of the component failure level. That's the method that we use. Target effects, of course, depends on, leads to what the target downtimes are. If you're looking for just interference, then the target downtimes are not going to be as long. In terms of protection, there's the Army back in 1992. The Army back in 1992, I don't know if the slide is showing yet or not because it's off my screen, developed this handbook called the Hardening Design Guide for Systems. We realized that there was a need to be thinking about how to protect our systems, not only what the potential weapon capabilities were. And what the High Power Microwave Design Guide does is it bases it a lot on what's the traditional techniques for hardening against electromagnetic pulse, but since microwaves are at much higher frequencies, there's a need for other types of hardening. And that is the reference there. It's now in DTIC, and it's also in DSIAC, and also the Joint Technology Office for Directed Energy Transition. Also, DTRA and JCOR generated a joint electromagnetic RF code that is now also in the electronic version of that. We have actually demonstrated to show that these techniques can work using an IFF transponder. We measured it to determine what power densities were required to cause it to fail. We put in hardening in terms of filters and limiters, retested it, and it was able to work. And most important, you have to realize anytime you do hardening that you do not affect the insertion loss for RF receivers and that type of thing. Okay, in summary, high power microwaves provide warfighters with a high probability of hit, the speed of light engagements, with the understanding that, of course, it's not instantaneous effects. It provides the warfighter with the ability to attack targets at a band with and without receivers and produce long-term effects. The effect levels depend very heavily on the source parameters and the target parameters, so it is very complicated, and effect levels typically have to be measured over some parameter space that you think you're of interest. The impact of effects on mission may be difficult to determine because you may not know whether the RF energy caused the system to fail or whether there was some sort of just natural system failure. And protection. It's been learned based from the electromagnetic pulse industry as well as HPM that if you try to do retrofit hardening after the fact, it's tremendously expensive. It can cost 20 to 90% of the total system costs, where if you do the RF protection at the design stage built in, the total system cost is much less. So the bottom line is you either pay now or pay later. With that, I thank you very much, and I'll try to take any questions that I have here in the next few minutes.
Thanks, John. All right, so I have unmuted the folks that are on the line. So if you do want to ask a question, hopefully you'll be able to ask that. Hopefully the unmute function worked. We did have a couple questions come through during the chat, and I appreciate there's a little bit of chatter going on in the chat, kind of a community discussion here. But one question here that was asked, John, and I think I know the answer, maybe you can elaborate on it, but is, can HPM be used against critical infrastructure?
Yes, the answer is it's been shown that, as you might expect, a lot of the critical infrastructure has a tendency in a lot of cases to use commercially available electronics, And that's one of the problems is it's been a while to try to explain and understand to people that critical infrastructure needs to be protected as well.
Okay.
I have a question related to that. Can you guys hear me?
Yep, go ahead.
Yeah. From time to time, you see some suggestions to use HPM and some sort of protection around civilian airfields. But it seems to me that that would be very risky against the civilian traffic you're trying to protect. Has there been any comment on that or thinking about that?
Yes, that's a very good question. There's no doubt about it. One of our major concerns is anytime you raise the power of an electromagnetic emitter, you've got the potential for basically fratricide and suicide. So you do have to look very carefully at how directive your beam is, how bad your side lobes are, how close other things are, so that you don't have electromagnetic interference and various types of, you want to have electromagnetic compatibility.
Thank you.
Another kind of question or topic that was brought up here in the chat, John, was about electromagnetic missiles. Whether that there's some research being done back in 1985. They've been used operationally, but not widely. Do you have any comment on EM missiles?
Well, I assume by EM missiles you're talking about an airborne platform that carries a high-power microwave type of source. And yes, that has been shown and demonstrated by the Air Force with the CHAMP program, which is the Counter High-Power Electromagnetic Advanced Missile Project, to show that you could potentially fly an airborne platform over a building with electronics inside and produce temporary and in some cases permanent upset. As a result, that's an area that initially a lot of people used to try to look at explosively driven RF warheads to do that type of mission, and it's still possible, but it's also the efficiency factor from the explosive to the electric energy is not that great. Now they're looking more at using battery packs and other types of compact power and energy systems to be able to power an HPM source long enough to do a mission.
Very good, thanks. Any other questions that anyone wants to just ask verbally or type in? Okay, we just had one typed in here for you, John. What's been done / what can be done to protect the individual soldier from HPM energy?
That's an excellent question. Generally speaking, as I mentioned before, the actual lower frequency high power microwave energy is not typically that dangerous to the soldier unless they're in it for a long dwell time. However, as we've talked about for the millimeter wave systems, there is concern that an adversary could use our type of technology for their advances. And yes, there is research going on I know specifically for the Army, at the U.S. Army Soldier Center, looking at materials that can be in a uniform to add face mask and things of that nature to protect the soldier. Basically little metallic types of either inks or wire fibers to try to be able to shield the individual from the millimeter wave energy. However, that's still going to be a very big challenge for the future.
Mm-hmm.
Well, I had a question. Can I ask?
Yep, go ahead.
Okay, this is Dave Chatterjee. I was the person who wrote on electromagnetic missiles. Actually, I came with the idea by reading some papers when I worked for summer faculty at the Navy Research Labs in Washington, D.C. And there I found out that from their reports and other papers that it is a special type of pulse, as Mr. Tatum was showing at the very beginning, which produces an electromagnetic wave by a very specific combination of this pulse rise time and everything that does not decay as 1 by r squared. The power density does not decay as 1 by r squared. and it can, in fact, be made significantly small. So I did some simulations, and I was very surprised. And that's why my question came in, that why did the government abandon this one? And the answer I got was it was the Gulf War tide, they took away all the money. So is there any revived interest, if I think of writing a proposal or whatever, is there anything that you would suggest that, because there are some theoretical and other practical questions that still need to be resolved? My view is that upon reading the literature, it needs to be revisited. That's my position. So I was asking that, is there any kind of interest in kind of renewing some funding or whatever to see if some of the basic approaches can be tackled? Thank you.
Yes. The short answer is we're always looking for any way to beat the range loss of the 1 over r squared range loss. Some of the concepts that have been considered is the idea of even using a basically ultra short pulse laser to try to generate a plasma channel that would allow RF energy to go down the channel. But there's also any other ways that people can think of that we can get more. That's one of the reasons why they're interested in, obviously, platforms that can get near a target to reduce the amount of range that the RF energy actually has to travel to the electronics. So I would say, yes, that it would be very interesting to hear what proposals that obviously this audience represents a broad base, and I'm sure you all have a lot of interesting and hopefully potentially successful ideas.
All right, just a few more questions here in the interest of time, although I appreciate all the questions that are coming in. John, the question was how to protect, or considerations for protecting radars or LiDAR sensors on ground-based vehicles.
Yes, one of the ways of trying to protect electro-optic types of sensors from RF energy has been thought of quite a bit. There has been various types of coatings that have been developed over the years that actually do have some attenuation for RF energy and still allows the visible energy to be able to exit and enter the electro-optic sensor. The problem there is that a lot of these tend to use some form of metal gridding as a kind of using the waveguide below cutoff principle. And as a result, if you're trying to protect or trying to have something where you're trying to put out high energy both from RF and a laser standpoint, that it's not easy to use those types of coatings. But for just general protecting electro-optic sensors such as IR and visible and that, there are electromagnetic coatings, and they're talked about in the hardening design guide.
Okay. And I'll probably just do one, maybe two more questions here that came through in the order. So I apologize for the folks we haven't gotten, won't be able to get the questions for. But next one here was, does EMP hardening by definition protect against EMP weapons?
No, that's an excellent question. As I tried to allude to, is that since EMP has a tendency to have lower frequency ranges, some of the techniques that are used in electromagnetic to protect against electromagnetic pulse are good, but at the higher frequencies, for instance, terminal protection devices that have long lead lengths and things like that that work well for EMP protection at the lower frequencies. At the higher frequencies, those look like transmission lines, and as a result, they may not. So just because a system is hardened, it's good. If it's hardened to EMP and EMI, then chances are that's a good start, but you have to look at the hardening from the frequency standpoint, and that's what the hardening design guide attempts to do, is look at some of these various types of traditional electromagnetic protection techniques, how well they work at high frequencies and what can be done at the higher frequencies to improve the shielding.
Very good. Thanks. Okay, last one here. How portable are HPM devices? Will they become more portable with better power generation and storage?
That's an excellent question. Yes, as depending upon what the mission is. Everyone working in the area of directed energy is concerned about the size, weight, power, and costs. The SWaP-C, or as my friend Dave Law at the Joint Non-Lethal Weapons Center says, the Joint SWaP-C squared, because it's also the other factor of cooling. So anyway, the important thing there is that there are a number of handheld devices that are being looked at for short range type of applications. But if you try to go to longer range applications against aircraft or whatever, there are improvements being done both in terms of typical prime power systems and pulse energy systems. But your antenna is still a big problem, because if you want typically high energy on a target, you need high directivity, and as a result that normally means a large antenna. Now there's some very interesting work going on with using the idea of fractal antennas and other types of materials that people are definitely trying to figure out how to get as much gain out of an antenna using special dielectrics to be able to reduce the physical size of the antenna, which in turn will also provide for greater portability.
Perfect. Well, John, thanks so much. We're over time, but all the questions are really good, so I appreciate you responding to them. For those who didn't get their questions answered, I would encourage you to go on DSIAC.org, and you can kind of submit a technical inquiry that way. You can email, again, myself, Brian Benish, and we'll get them answered for you. Again, we offer a free service of 4 hours of information research for any technical question that might come through or you might have for us. So I'll be happy to support you however we can. John, thank you very much. Appreciate it. Again, this webinar has been recorded, so we'll post it online and make sure it's available. So if you guys want to check it out again, it'll be public. So thank you very much for participating, everybody.
Thank you. I appreciate the opportunity to talk to this great audience.
All right. Thanks, John.